Okay. So in this problem, we need to find the shear force and the bending moment equations, as I mentioned earlier. And from our previous discussion, you'll recognize that we need two sets. One that's good over this continuous range from 0 to 12, and the second set that's good from 12 to 20. In both cases, I may need the reaction, so I'm going to go ahead and find my reactions to get started. So I'll come over here and I'll draw a free body diagram of the whole structure. And I will assume, again, that I have positive shear and positive bending moment. And these are at points A. And then at the free end, there's a 20 kip force. And then I have a concentrated equivalent force to represent the area under the rectangular section, which is what? Base times height, so it looks like it's 48 kips. And the distance from A would be how far to the centroid? 6. Yeah, half the distance, or 6. So then the remaining distance would be 14. I think that's all we need. Relatively simple set. So I'll go ahead and sum the moments about point A and make sure it's in equilibrium. Again, right-hand rule for my sign convention. So starting here at A, what kind of moment is this in my sign convention? Negative. So I have negative moment at A. What about the 48 kip? Positive or negative moment? Negative. Has a moment arm of 6. What about the 20? Well, same as the 48. Negative. So I can now solve for my moment at A. It looks like it's going to be negative. It's nearly 700. What is it? 688? 588? This is the point where you get out a calculator and type in some numbers, starting with 48 times 6 plus 400. Huh? 688? 688. Can I get a confirmation from Mr. Copeland's mental math? 688? I think I said 588.
I think you said 6 first.
Did I say 6? Well, thank you. All right, so let's go ahead and finish and get the... we'll sum forces in the y direction so we can get a approximation for our shear. So that force is up, shear at A, and then we have acting down our concentrated equivalent force of 48 and our applied force of 20. So the shear at A looks like it is 68. Okay, so let's come over here and we want to cut the structure at some distance x, and you want to work the left side or the right side. You can do either. I feel the left side is going to be a little less demanding of you. The load is consistent. Here it kind of starts and stops. So let's do the left side. So I'm going to write that this is going to be good for x between 0 and 12. So that means this can be any time between 0 and 12. And whenever we stop, we're going to look at the left-hand side. So this is what my free body diagram is going to look like. We found that the shear was positive and 68 kips, and that the moment was negative, and it was 688 kip feet. And then I'm going to assume positive shear and positive bending moment. And then I have the concentrated equivalent force for that uniform load. Now for a distance x over, what's the concentrated load, the area under the curve? Base times height, which will be what? 4x. So this force will be 4x. And the distance from the corner, or from the cut, the distance divided by 2, the distance is x, so this should be a distance of x over 2. Everybody see that? So now it's just back to our statics. So we'll sum moments about the cut. So starting here on the left, I've got a positive moment. The 4x creates positive moment about the cut. That's the force. And its moment arm is x over 2. Then you hit 68, which creates negative moment. And what's its moment arm? X. And then you have the 688 at the end, which is positive. So when you solve for the moment, which will be a function of x, let's see, you'll get this cancels, so you'll get negative 2x squared plus 68x minus 688. Let me put a bracket around all that and note that the units are in kip feet. So does that make sense? What do we know about the moment between 0 and 12? Do we know the moment anywhere? What is the moment at A? Yeah, so we know that the moment when x equals 0, according to our calculations, should be negative 688 kip feet. And is it? Does our equation give us that? Yes, it does. But we don't have any place else to check because this equation is only good to 12 feet. Do I know the moment by inspection anywhere between 0 and 12? At this point, the answer is no, I don't. So let's go ahead and find the shear now. We'll sum forces in the y direction. So the shear force is acting down, minus V. Our 4 kip force is down. 4x force is down. And our 68 kip force is up. So it looks like the shear as a function of x is equal to negative 4x plus 68. And that's kips. Does it match what we know about the shear? Well, we know the shear at x equals 0 should be, according to our calculations, 68. Do we get that? X equals 0, 68. We also know informally that if I take the derivative of the moment with respect to x, I should get the shear. Is that true? If I take the derivative of my moment equation, do I get the shear?
It's true. Yes.
True. I like that. Check. So far, seems so good. Now what? I got to go and redo this problem from 12 to 20. Now at this point, I'm going to jump up and I'm going to assume a cut here. And again, x is measured from the far left to this point. Now, what section do I want to look at now? Do I want to try to work the left side with all this or the right side? I say the right side is better. Now, if the distance from the left side to the cut is x, what's this distance right here?
20 minus x.
20 minus x. So I'm going to draw my free body diagram of the right side of my structure. I'm going to place my 20 kip load on the free end. Now, on the cut surface, I'm going to assume positive shear and positive bending moment. Now remember, I'm measuring X from the left to the cut. So as we mentioned before, the length of my element now is 20 minus X. So now, that's a pretty simple free body diagram. I'll just sum moments at the cut, like I've done before. So starting here with my right-hand rule as my equilibrium, as my sign convention for equilibrium, the moment's negative. The 20 kip force also creates negative moment with a moment arm of 20 minus X. Everybody see that? So now the moment, which is a function of X, is just going to be minus 20 times 20 minus X. Now for me, you can just leave it like that. You don't need to expand it. If you feel more comfortable doing that, you can. It's okay with me. Now, what do we know about this? What do we know about the moment on this section? Well, what's the moment at B? There's no applied moment, so it must be 0. So the moment at X equal 20 should be 0. Is it?
Yes.
Yes. Now, there's one other thing we can do. With this moment equation, these two moment equations share a point. What point do they share in terms of X? They're both good at X equal 12. Okay? So I'm going to go back and call this moment 1, shear 1, moment 2. So moment 1 at X equal 12 should equal moment 2 at X equal 12. So I'm going to let you guys figure that out. I can do the second one easy. I put 12 in here, I get 8. 8 times that's negative 160. Somebody else go check that real quick and tell me if it's negative 160. And while you're doing that, I'll go ahead and continue and sum forces in the Y direction for this second body and find my shear. So shear is acting up and the 20 kip force is acting down. That's a pretty easy problem to solve. So it looks like the shear in the second function, or second free body as a function of X, is 20 kips. Okay, great. So backing up a little bit, that means I can come over here and say, yes, this is true. One more thing I can do is look at the shear. Oh, by the way, does the derivative of the moment with respect to X equal the shear for the second set of equations? The answer is yes. And the final thing I could do is I could say the shear at 1 at X equal 12 should be equal to the shear at 2 at X equal 12. There's not a point load there. It's not like we're going from one side to the next where there would be a dramatic change. So you can see the shear at 2 is 20. And when I put in 12 here, you get 20. So that also checks out. So I got lots of green checks. So I feel pretty good that this set of equations for moment and shear in the first section from 0 to 12 and moment and shear for the second section from 12 to 20 is good. Any final questions or comments? I like this problem. This is a testable problem.